Welcome to integration. Integration is the big daddy of calculus. The fundamental theorem of calculus states that integration is the reverse of differentiation, and that's a really good way to think about it. It's a lot more than that, but that is a really important aspect of it. So when you're looking at an integral, you want to be thinking of it as an antiderivative. In other words, you're looking at something which has already been differentiated, and it's your job to try to reverse that process and figure out what it was that you started with that produced this derivative. It's a lot like factorizing a quadratic as opposed to expanding brackets. The first thing you learn is how to expand brackets, and then once you've understood that process thoroughly, you're then in the right place to attempt the more sophisticated and more creative process of attempting to factorize a quadratic. The same is true for differentiation and integration. It may feel like differentiation is quite complex, and it definitely can be, but at root, it is a series of processes which you can apply, and you can be confident that you will be able to differentiate any function. I can give you a function multiplied by another function divided by something with a function inside, another function inside that, and with a combination of product rule, quotient rule, chain rule, you can break it apart and evaluate the derivative. Integration is not always as straightforward. Often it's very hard to identify the function which would differentiate to give a particular function, just like there are some quadratics that are very hard to factorize, even though you could routinely expand out any pair of brackets I gave you. And there are some integrals that are not possible, at least not with elementary functions. There are no functions you could write down involving the standard things that you've got in a scientific calculator that would differentiate to give you e to the x squared, for instance. And therefore, in some sense, there isn't an integral for e to the x squared. We have to basically create a new function to describe that. We're not going to get into that in this course. But that's also reminiscent of quadratics, because there are certain quadratics you could write down that cannot be factorized. Even if you allow yourself all sorts of horrible numbers like surds, there are some that just don't have any roots, and therefore they don't have any factors. And until you create a new number system for it, you won't be able to deal with those quadratics. Very similar things happen with integration. But because integration is the reverse of differentiation, it's really important that you're confident with differentiation first. Otherwise, it'll be like trying to learn how to divide before you've learned your times tables. So have a go at these 5 questions, and then we're going to run through them briefly before we dive into integration. And we'll come back to them again later in the video and find out how we can reverse the process so that we end up integrating. The first question, sine differentiates to cos, but because we have chain rule involved, we multiply by the derivative of whatever that function was inside. Sine of something becomes cos of the same something, but we multiply by the derivative of the something. Y equals 5 to the x, this is an exponential function, and if it was e to the x, it would just differentiate at e to the x. But we have an adjustment factor we have to incorporate here. If you've forgotten y, think of 5 to the x as being the same as e to the power of ln 5 times x. That differentiates to e to the power of ln 5 times x multiplied by the adjustment factor ln 5. But e to the ln 5 times x is 5 to the x. For question 3, you'll find it helpful to consider that as 3x add 7 to the power of a half. And then it's clear that we've got some chain rule involved. The inner function is just linear again. It's 3x add 7. But the outer function is something to the half. So we bring the half down in front. We reduce the power by 1. But there's another thing going on here, which is a 3 has appeared. It's not just a half of 3x add 7 to the minus a half. It's a half of that stuff to the minus a half multiplied by the derivative of the 3x add 7. Question 4 is similar. We've got a function inside a function. We can differentiate ln of something. It just gives us 1 over the something. But then we need to multiply by the derivative of the something, which in this case is 2x. And cos to the 5x. Remember, this weird notation for trig shouldn't cause any confusion for you. We've been using it lots, so hopefully you're getting familiar with how it works and why it's not the same as the notation used for cos to the minus 1. Cos to the 5x means cos x raised to the power 5. And if we've got something raised to the power 5 for our outer function, then we'll get 5 lots of that something raised to the power 4. After that, we just need to multiply by the derivative of the something. which is minus sine x. So we get 5 lots of the something to the power of 4 multiplied by the derivative of the something. So we have 5 cos to the 4x multiplied by minus sine x. This slide would not be complete with a bit of XKCD. Just to give you some sense of how differentiation and integration relate to one another, this is what we've done so far. Chapter 9 in a nutshell. Differentiation is the process of applying a few rules that you've learnt, a couple of tricks along the way, and you should be able to construct an answer. Integration will feel a little bit more like this. So there's a couple of useful standard methods that often work quite well, but integration has such a wide and rich variety of different types of functions that every new integration question is a little bit of a miniature problem-solving process in and of itself. You will learn to get confident with lots of different types of integrals if you work hard at this, just like you get confident with lots of different types of problems when you solve lots of problems. But you will find it a very different process to differentiation because there's so many different things you could try, and there's no guarantee that what you're attempting will work. You'll go through the process of trying something, it not working, or it making things more complicated and going around in circles, trying different things. There are lots of things that we can point you in the direction of, helpful tips for particular types of functions you might deal with, but there's also loads of functions you can create just by making a small tweak to a function that you can integrate, and you'll turn it into one that maybe you can't integrate. Maybe you can, but you need to think of the right type of substitution to use, or you need to recognize an appropriate way to rearrange it. So it's a great topic, but don't be surprised if this feels really tricky compared to differentiation, because sometimes it will. There's a lot of bits that need to be in place before you can comfortably look at an integral and know what to do with it. Let's start by writing down a few key results. Each of these is a derivative result that we've already seen. We've demonstrated that these work. We're just going to make use of these to construct a corresponding integration result. So I'll start you off. For instance, the first one, if we know how to differentiate powers of x, and what we get is another power of x, then we can integrate a power of x. And we follow the reverse procedure, and it works just fine. Instead of bringing the power down in front and reducing the power by 1, we increase the power by 1 and divide by the new power. Don't forget the plus c, the constant of integration. Have a go at these next ones, and then when you think you've got the results, unpause the video and see if they match mine. So for sine x differentiating to cos x, the comparable result would be cos x integrating to sine x. For the next one, I could have written the integral of minus sine x is cos x, but it's more sensible to learn the integral of sine x, and that happens to be minus cos x. One way to remember this is the mnemonic sine integrates negatively with the sin from the word sine. It's not the prettiest and most elegant way of remembering it, but if you recall that sine differentiates to cos, then hopefully the reverse process will stick in your head that sine integrates to negative cos. So still sine goes to cos and cos goes to sine, but there's a minus that gets thrown in there. And for differentiation, that happens when you differentiate cos. For integration, it happens when you integrate sine, because you're reversing the cos differentiating to minus sine result. E to the x is a breath of fresh air. E to the x will integrate to e to the x, because it differentiates to e to the x. And for ln x, we get something like this. It's not quite the same as this, and there will be a video detailing a bit more carefully exactly why, but what we need to include here are modulus signs. ln of mod x, not just ln of x. That's basically to allow us to deal with all of the 1 over x graph, rather than just the positive bits of it, but more on that in a later video. So, without further ado, let's look at what integrals are provided for us. We've got a few of the standard ones, and the ones from the previous page you'd be expected to memorize for yourself. No one's going to be telling you what cos integrates to, so that needs to be in your head. But the book does have 2 pages that include standard results. We've got page 7, where there is a table of integrals, f of x and the integral of f of x. So you can look up your integral on the left and get an answer on the right, such as the integral of sec squared is 10. But on page 6, we've also got the differentiation section. And although it may not seem like it, this is also really helpful for integration. Turns out some results appear in the differentiation table, but they don't appear in the corresponding integration table. So it's worth being aware of that. If you are trying to integrate sec x tan x, for instance, you'll notice it doesn't appear on the integration table, but it does appear on the right-hand side of the differentiation table. Now is a good time to pause and have a go at a few questions from 11a. You don't have to do all of them, but you might find it helpful to crunch through quite a few so that you build some confidence and fluency with the process of working backwards. It's a good idea to get stuck into some simpler questions where you're not having to overcomplicate things by reversing chain rule or anything at this point. We're just going to focus on, can you take a function that you're already familiar with and do the reverse process with it instead of the differentiation you're going to be integrating. Now let's return to the derivatives that you calculated at the beginning. I've included them again up here so you can reference them in case they're not right in front of you. What I'd like you to do is make use of these results and do a bit of reverse engineering. So if you know how to differentiate sine 3x and you get something involving cos 3x, maybe you can see how you could integrate cos 3x. Have a go at these 5. And when you think you've got some answers, try differentiating your answers to check and see if you get back the thing under the integral sign that you were trying to work with at the beginning. All right, let's check. Cos 3x is a third of 3 cos 3x, which means it must come from a third of sine 3x. The simplest way to think of this is in terms of a vertical scale factor for the function. So if sine 3x is scaled down by a factor of a third, so that the height is now just a third of what it was, then the gradient function will also be scaled down by a factor of a third. If you squash a graph, you squash its steepness as well. So anytime you're doing an integral of something which is just a scaled up or down version of something you already know, you can adjust it following the same scale factor. The next one for 5 to the x. Well, if 5 to the x ln 5 is the derivative of 5 to the x, then by doing the opposite, by dividing by ln 5, we get the integral of 5 to the x. You can check that this works. If you have 1 over ln 5 multiplied by 5 to the x and you differentiate it, well, the 1 over ln 5 is a constant, so that stays put. And 5 to the x differentiates to 5 to the x ln 5, at which point the ln 5 and the 1 over ln 5 cancel out and leave you with exactly the thing you had under the integral sign. For the third one in that column, we have 1 over root 3x add 7. Well, the result that we got there that's related to it is the 3 over 2 lots of 3x add 7 to the minus a half. So if we think about our integral more in those terms as 3x add 7 to the minus a half, we can see that the derivative in question 3 was 3 over 2 times the size. Therefore, our integral will have to be 2/3 of the size. We want something which is 2/3 the size of the thing we already know about, so we just multiply by 2/3. A similar thing happens with the next one. Instead of 2x over x squared add 4, we've got x over x squared add 4. We've got an integral which is half the size of the derivative we know about. Therefore, the answer will be half of the original function that we were dealing with in question 4. For sine x times cos to the 4x, that's very similar to what we're looking at in question 5. All that's happened is the function we're trying to integrate is minus a fifth of the size of the derivative we had in question 5. So the answer will be minus a fifth of the original function. Look carefully at these and think about how they work, and hopefully you'll start to see that you can go beyond trying to work backwards, which can be a real headache, to thinking in terms of just dividing by the adjustment factor that would have appeared when we originally used chain rule. That's possible for the cos 3x, and it's possible for the 1 over root 3x add 7 as well. For the others, there's a slightly more sophisticated process going on. But you can still do something called integration by inspection, which basically means you already have an idea of what would differentiate to give this thing, and then you adjust it to make it work. It's a bit like if I ask you to work out the square root of 81 and then ask you how you did it, your answer will probably be, well, I knew that 9 squared was 81, therefore the square root of 81 is 9. In other words, the way you answer it is by knowing the answer already. That's why integration by inspection can feel a bit like cheating. If somebody recognizes a result, they can write it down straight away, but they can't explain how to do it other than to say, look, it works. When you differentiate it, it goes back to what it was before. But there will also be another method called integration by substitution, which is a more formal way of effectively reversing chain rule, but it's a bit more powerful than that. And that's the method I would normally use for those three questions in the middle there, the 5 to the x over x squared, and 4, the sine x cos the 4x. In fact, 5 to the x is a fairly standard result that you can use. I would probably turn it into e to the ln 5 times x, and then reduce it using the fact that it's something linear inside. But we'll get to that in a moment. There's a bunch more questions that are similar to this that I'd like you to have a go at. These are in the worksheet that should be attached. And each one starts out by differentiating a function that you're familiar with. They're slightly different to just the standard e to the x or sine x. They've got some extra bits in like cos 2x or tan 5x. But once you've got a result, that should allow you to find a corresponding integration result. And then you might be able to construct for yourself a more general result by replacing a 4x with a kx. Give those a go, and on the next slide, I'm going to go through the answers. So let's take these one at a time. X to the 5, we know how that differentiates, 5x to the 4. Well, that means that x to the 4 must integrate to a fifth of x to the 5. Now, you can think of that as reversing the differentiation approach, or you can think of it in terms of following the standard rule for integration that you've already learned. You can increase the power by 1 and divide by the new power. It will be good if we can start thinking in similar ways for the rest of them. In other words, instead of trying to work backwards in our heads, we're learning the language of integration directly. So because e to the 3x differentiates to 3e to the 3x, when we integrate e to the 3x, we still get e to the 3x. We just divide by the derivative of 3x. And if we were integrating e to the kx, we divide by the derivative of kx. And that works fine, provided the derivative of the thing you're talking about is a constant. We're going to see why it works with a constant and why it doesn't necessarily work with others in a moment or two. 2 to the x differentiates to ln 2 to the x. If you integrate, you have to remember to divide by the adjustment that 2 to the x produced. That's easier to see if you rewrite it in terms of e, but it's a useful result to have on hand in case you're dealing with exponentials. ln 4x becomes, well, this one's a slightly weird one, isn't it? Because ln 4x differentiates to 1 over 4x, but then you multiply by the derivative of 4x. So you get 1 over x. And in fact, the integration I've asked you to do in this row is slightly deceptive because you don't just perfectly reverse. The derivative of ln 4x is not 1 over 4x. So the integral that you're finding is actually going to have to be a quarter of 1 over x. One way to see why this should be true is to think about log rules. If you have ln of 4x, it's equivalent to ln 4 plus ln x. And ln 4 is just a constant. So when you differentiate, the constant disappears. And that's also the reason that I've got two different valid answers here, a quarter ln 4x plus c or a quarter ln x plus c. The c in each one is not necessarily the same. That's the secret here. If you tell me that you've got an answer of a quarter ln 4x plus something, and I say, well, I've got an answer of a quarter ln x plus something, they're not necessarily wrong or incompatible just because a quarter ln 4x is different to a quarter ln x. They are different, but they're only different by a constant. So if you add the right number to yours, you'll get mine. If I start with a quarter ln x and I add a quarter of ln 4, then I'll get to a quarter of ln 4x. So the constant may be different and an integral may look quite different, sometimes a very different form, especially with trig, if you've used a different approach to get your integral. but it's not necessarily completely wrong. It may be absolutely valid, but scaled up or shifted up, rather, up or down from the alternative form. That's taken into account by the constant of integration. So in general, if you have 1 over kx, you can think of this as being 1 over k times ln kx, or 1 over k times ln x. Either of those is fine. What I'd be tempted to do in that case is take out 1 over k as a common factor and call it 1 over k times the integral of 1 over x. And then the integral of 1 over x is ln x. And then I still have the 1 over k at the front. For the next one, sine 3x, we can differentiate sine to get cos, but the 3x we need to multiply by the 3. The equivalent for integration is to integrate cos in the normal way. Cos integrates to sine, but then we divide by the derivative of the 3x. And in general, we divide by the derivative of whatever's inside, provided that thing is linear. For the next one, it's very similar. We get a minus, so we need to remember that sine integrates to minus cos, but we're going to divide by 2 because 2x has a derivative of 2. And the same thing happens if it's k. For tan 5x, the derivative is sec squared 5x multiplied by the derivative of 5x. So when we're going back the other way, we get something which is a fifth of the size. Hopefully, this general pattern is becoming a bit clearer to you now. So if it's something you can readily integrate, and the only niggling feature is something linear inside the function, then you can divide by the derivative of that thing, and it won't affect your answer. All of these examples on this particular slide are linear things that don't have a constant, just so they fit more conveniently and they don't complicate things too much. But if you've got a sine of 2x plus 3, it just integrates to cos of 2x plus 3 with a minus in front and dividing by 2, because the derivative of 2x plus 3 is still 2. So our final result for sec squared, this in fact appears in the formula book, and here's the last thing I want to mention on this slide, is that even if you get a little mixed up with the effect of having something inside, do you multiply, do you divide? If you have a sneaky peek at the formula sheet, you'll see that whenever they quote one of these standard results, like the result for sec squared x, they actually quote it in this format that's given at the bottom right, sec squared kx. So you can see the effect of the k. It remains there, it's preserved, so it's tan of kx, not just tan of x, but it also impacts the total size of the integral because you have a 1 over k term at front. Now let's look in more detail at what goes on when we integrate a function of something linear. In general, it's not particularly easy to reverse the chain rule process. We can do it, it will require integration by substitution, but provided the inner function is nice and straightforward, if it's something linear, then it is okay to reverse the process. I'm going to talk you through how that works and why it works the way it does. So chain rule tells us that if I have a function f of ax plus b, I can differentiate that function, so dy by dx would be f dashed of ax plus b, provided I also multiply by the derivative of that inner function, in this case a. So I've got a times f dashed of ax plus b. Now, classic trick, we're going to do this also for product rule when we work on integration by parts. What we're going to do next is integrate both sides of that final expression we've got. The integral of dy by dx with respect to x is y. So we're just reversing that process, but I'm writing it out explicitly as an integral for this first line. And the integral of the right-hand side will just be the integral of a f dashed of ax plus b with respect to x. So now we're going to recognize that if you have dy by dx and you integrate it with respect to x, you get back to y. Another way to see this would actually be to think about the dx in the integral cancelling with the dx in the derivative dy by dx. And then you're just doing the integral dy, so it's an integral with respect to y now. And in fact, because there's nothing else there, you can think of it as the integral of 1 dy. You're integrating the expression 1 with respect to y. And if you integrate 1 with respect to x, you get x. If you integrate 1 with respect to y, you get y. It's a slightly more convoluted way of demonstrating it, but if you differentiate y, you get dy by dx, and if you integrate dy by dx, you get back to y. So we can write this as y equals something. And I want to emphasize the a that's in front, because on our next line, we're going to pull that a out. Y is the same as f of ax plus b, so to make a more convenient rule, I'm going to rewrite y as f of ax plus b, the original function. And the original function is what you get when you integrate f dashed of x plus b with respect to x, and then multiply by a. This is the really important bit. We can pull that a out, and that allows us to divide both sides by a and get our final result. Now let's read this from right to left so we can see what it's telling us. If you are integrating something, a function which you know the integral of, because we're looking at f dashed, that's what's inside that integral, a function which you know the integral of, f dashed integrates to f because f differentiates to f dash, then we can just integrate it directly. F dashed of ax plus b becomes f of ax plus b, with the adjustment of dividing by a, dividing by the derivative of that linear term. There's a few questions on here that you can try. A couple of points I want to make before you dive into those. The a that got pulled out there, this is pretty important. The whole reason that this method works is that that is just a number. A is going to be 2 or 17 or 42 pi. And it's a number that you can pull out of the integral, because if you're integrating 7x squared, it's the same as integrating x squared and then multiplying by 7. And the reason this works is also the reason it doesn't work if that function inside, the inner function, is not linear. If we've got ax plus b, when you differentiate, you get a, and that's a constant. But if you had some other function, you wouldn't get a constant when you differentiate it, and you wouldn't be able to pull it out. If you're integrating something that's been multiplied by x, for instance, or by e to the x, you can't pull that out of the integral sign, because as x changes, that's going to change. It needs to be included in the integral. Whereas if it's just a constant, you can pull it straight out. Here's our final result. You should be able to have a go at those questions now from 11b, making use of that idea. It should start to feel a bit more sensible. The more you do, you'll start getting used to the process, and it should remind you a lot of the simple chain rule questions, just done in reverse. Here's an alternative version for the notation. Sometimes you see a capital F used for the integrand, in other words, the bit you get after you integrate. So if you want to think of it as I'm integrating a function, then what do I get? I get the integral of that function applied to the same input, ax plus b, but I also divide by the derivative of that input. If that's a more helpful way for you to think about it, then by all means use that. We're going to finish off with a couple of examples. This one looks quite daunting, but it's not as complicated as it might seem. There's a few key things you want to look out for. The first thing is this. Anytime you see trig appearing, you should keep one eye on the formula book, because either in the integration section or the differentiation section on pages 7 or 6, you may very well find something which is either exactly the same as what you're dealing with, or something similar enough that you can convert what you've got to an appropriate form. In this case, sec squared is what we call a standard integral. It's in the list. It's one of those that you should look at and say, oh, I'm pretty sure that one is provided for us. Have a look in the list. There it is. Sure enough, sec squared will integrate to tan. So we can make use of that. Now they've got a sec squared kx version. We've got sec squared of something else. But the fact that our something else is linear means that we don't need to worry too much about it. It is a chain of functions, but the inner function is linear. We can think of the outer function as being sec squared x. We don't need to think of it as being sec x inside as something squared, because sec squared x, all on its own, will integrate to tan x. We know that already from the standard integral provided in the formula book. So we just do it. Once you recognize those pieces, it becomes one step. Sec squared becomes tan, but the inside, pi minus 2x, remains there. It's preserved inside the tan, pi minus 2x. The only difference is that we're going to divide by the derivative of what's inside. The derivative of pi minus 2x is minus 2, so we've got 1 over minus 2 inside there. Now, because this was a definite integration, we've got limits to apply. And one thing I want to point out here is that if you have a limit of 0, you might have got used to the fact that whatever has a limit of 0 just disappears. Now, in this case, it does, even though this is a weird, complicated function, but it's by no means obvious that it should. The reason it has in the past for you is that you've been integrating polynomials, and no matter what polynomial you integrate, you'll always end up with another polynomial which has no constant term, because any constant that was in your original polynomial has become an x term. The constant would have been dealt with by a constant of integration if it was an indefinite integral, and wouldn't be there at all for a definite integral. So subbing in 0 would have given you a 0. But that's not the case necessarily with all functions. Certainly something complicated like this could potentially have given you something different. But we just substitute the values in and we simplify. Tan of 2 pi by 3 we can find, I believe it's minus root 3. And tan of pi is 0, so that bit does disappear, and we get root 3 over 2. Worth noticing at this point, we've got exactly root 3 over 2, and we leave it as root 3 over 2. There's no advantage to writing 0.866 unless you happen to be testing your result with a calculator. It's perfectly possible to generate a numerical approximation to this value by typing this into the calculator. You'll have to type it in as 1 over cos of something in a bracket squared, but it's certainly possible to do it. That will verify for you that your solution is correct, because if you get positive 0.866, that's going to show you that root 3 over 2 is likely to be the right answer. But it's certainly not going to get you marks if that's the only approach you take. You're not going to get the marks for some decimal result, and you won't get any marks if your result is derived purely by using the calculator. If you're asked to integrate, they want to see evidence that you've integrated the function and that you've got a final result which is given in exact form unless they ask for something different. Our final example may also look horrible, but there is a ray of hope. If you look closely, you'll find that the functions inside are linear. It's not just e to the x, but it is e to the power of something linear. It's not just 5 over x cubed, but it is 5 over something linear cubed. So that should give us hope. For e to the x, we know that e to the x integrates to e to the x. And the power being linear means that all we'll need to do is adjust by dividing by the derivative of that linear power. For the next bit, it can be helpful to rewrite this in a more sensible index form so that you can identify it more easily. This is a chain with an outer function of minus 5 lots of something cubed to the minus 3. And the inner function is just linear. It's 4x add 7. So if you can integrate minus 5x to the minus 3, then you can integrate minus 5 lots of anything linear to the minus 3. You do the standard thing. You increase the power by 1, divide by the new power. The minus 5 will stick around at the front. The only difference is, at the very end, you're also going to divide by the derivative of that linear function that was inside. Let's see what it looks like. There's e to the 3x minus 1 being integrated to give also e to the 3x minus 1, but divided by 3, the derivative of 3x minus 1. Then we're taking away something to the minus 3 integrated. And you can see that in here. It looks complicated. It looks rather messy. But this piece here, 4x plus 7 to the power of minus 3, this bit, if you do the straightforward integration process, you increase the power by 1, becomes minus 2. You divide by the new power, you're dividing by minus 2. And I'd encourage you to write it out in full like this, because it's very easy to make mistakes with numbers when you're multiplying or dividing, changing sign. Write out a full version unsimplified before you start combining things. Now we still have the minus 5 that was kicking around in front, so that needs to stay there. That minus 5 will still be here. But the other thing we have to not forget is that because this wasn't just x to the minus 3, it was 4x add 7 to the minus 3, we need to make sure we divide by the derivative of 4x add 7. Once we've done all of that, all that remains is to simplify it a little bit. So I've rewritten this so that instead of something to the minus 2, it's on the bottom of a fraction with a positive power. Because I'll be substituting numbers in, it'll make it easier for me to not make mistakes, I think. The two negatives from the minus 5 and the minus 2 have cancelled out, and then the 4 and the 2 combine on the bottom to give an 8. Once we've got that, we can substitute numbers in. Remember, like we said last time, just because you have a value of 0 being substituted in does not necessarily mean you'll get a result of 0 from your integrand. The stuff in that big square bracket will be non-zero in this case, even though x is 0. Part of that is because that's what exponentials do. If you have e to the power of 0, it's still going to be 1. And in this case, it's not even e to the x, it's e to the 3x minus 1. So we end up with a third of e to the minus 1. And then the next bit is not going to be 0 because it's not just straightforward powers of x either. It's actually 4x add 7 on the bottom. And although the 4x disappears, the 7 is still live and kicking, and we have an 8 and a 5. So all of that combines. I recommend you don't chuck it all in your calculator at once, because then all you'll get is some horrible decimal that is not the correct answer. Your decimal is just very, very close to the correct answer. What you want to do is combine the exponential bits, because they cannot be written in a nicer form than just as exponentials. And then the rest of it, put that in the calculator, simplify it down, and you'll end up with a nice fraction. Then you can write them like this. This is the exact value of the integral that it asked about. Any other form wouldn't be quite the same. But like we saw with the last one, if you want to verify your result in an exam, there is nothing stopping you from using the integration functionality of your calculator. You'll have to be careful typing in the equation just as it appears in the question, put in the limits of 0 and 2, and then compare the decimal that it churns out to the decimal you get when you type in your exact value. That doesn't prove they're the same, but it will convince you and help you to see that you've not made any little mistakes along the way. If it comes out looking wildly different, go back and look carefully, particularly at any lines where you've had to divide by the differential of something linear, or anywhere where you might have cancelled out a negative sign when you shouldn't, or you haven't cancelled out a negative sign when you should.